Hello everyone, Victor from OrganicChemistryTutor.com is here, and in this video I want to talk about an interesting reaction of aldehydes called the benzoin condensation. The reaction name originates from the name of the product that you are going to get when you perform this reaction on the benzaldehyde alone. Okay, so here we have the general scheme for the benzoin condensation, and this is what we call a classic example of the benzoin condensation, where the two molecules of benzaldehyde, so I have two equivalents of benzaldehyde over here, where those two equivalents react with each other using the potassium cyanide as a catalyst. We can use other catalysts in this reaction, and there are plenty of examples in the literature that do indeed use other catalysts. And all of those catalysts are going to have two important features. The first feature is that they should be nucleophilic, and the second feature that all the catalyst species that you may see in the benzoin condensation reaction, they all are electron withdrawing groups, they all have electron withdrawing properties, because that is very important to stabilize the intermediate. And we'll look at the mechanism for this reaction in just a few moments, so don't worry if it doesn't make much sense right now. I'll specify where and why it comes into play once we get to that point. The other components of this reaction, here it's just water and ethanol, that is basically just a solvent mixture. The nature of solvent is only marginally important in this case. Ideally, it should be some sort of a polar product solvent to facilitate the proton exchange in this reaction mechanism, and also it should be effective in solvating the polar particles that we have in this reaction. So usually an alcohol-water mixture is probably the best one and the most commonly seen for the benzoin condensation type of reactions. Alright, so here we have our mechanism in details. The first step, the reaction starts by the attack of the nucleophilic catalyst on the carbon of the electrophilic carbonyl. If you need a refresher on what an electrophile and what the nucleophile is, I have a video on that too, and the link for that is going to be in the description below. Alright, so the first step here, in a nutshell, is nothing more than just the formation of the cyanohydrin, which is a very common reaction of aldehydes and ketones. One other thing that I want to point out in this particular case, that when we are deprotonating water, we are going to be forming an OH-, which comes into play in the second step of this reaction, so this is where we get the base for this reaction, although initially we didn't have any. And in the next step, we are going to use that base that we have formed in the first step, so that OH- came from the first step of this mechanism, and we are going to be using that base to deprotonate our cyanohydrin and form the nucleophilic species. And this is where the electron withdrawing nature of the catalyst comes into play, because without the cyanide, this hydrogen, this proton over here, would not be acidic enough, and it wouldn't be possible for a mild base like OH- to pull it off. Another important thing I want to point out about this reaction is the polarity reversal, or the Umppelung of the carbonyl. Normally, we would have a very significant partial positive charge on the carbon of the carbonyl compounds, because if we look at our CO double bond, we have a very significant difference in the electronegativity between carbon and oxygen. Carbon normally has electronegativity of about 2.5, oxygen has electronegativity of about 3.5, so that gives a very significant delta plus charge on the carbon. So that is a normal charge on the carbon. However, in this particular case, we have a negative charge on the carbon over here in the resonance contributor, which makes that carbon nucleophilic, which is unusual because normally carbon of the carbonyl is going to be electrophilic. And the technique in which we invert the charge on an atom in a molecule is called the Umppelung or Umppelung principle, which literally translates from German as an inversion of polarity. So now, once we have a nucleophile, that nucleophile can react with an electrophile, and an electrophile in this particular reaction going to be the other molecule of benzaldehyde. While several different nucleophilic attacks are generally possible in this case, the formation of the carbon-carbon bond in the most thermodynamically favorable process in this case. Thus, we're not really going to look at other possible steps in this reaction. Although they are possible, this reaction is an equilibrium, so even if other nucleophilic attacks happen, they will simply revert back to the starting material and we will eventually form the carbon-carbon bond here. And finally, we are going to regenerate our catalyst by doing the leaving group dissociation. I'm technically combining the two steps here, doing the proton transfer, this part, and the leaving group dissociation, this part. So I'm technically combining both of those steps in one. And whether it actually happens in one step or it's two separate steps, that's kind of up to a debate. And at least I couldn't find any literature describing that in detail, so if you have any sources I could look up, let me know in the comments below. So overall, if we look at the complete mechanism, we're going to see something like this. And to do a quick recap here, we started by forming a cyanohydrine, which is a species over here. Then we deprotonated that cyanohydrine, we pulled this proton to make a nucleophilic species, which then reacted with benzaldehyde, formed a new carbon-carbon bond, and we finished this reaction by kicking our leaving group out, forming the final benzyne. One other thing that I want to point out here, that when a chiral catalyst is used and not just a simple cyanide, we can potentially increase stereoselectivity in this reaction and make a very specific enantiomer or diastereomer in this molecule, depending on the nature of the molecule. So that can potentially be very important, and I'll talk about that in a moment as well. So here are a few more examples of the benzoin condensation. And in this case, interestingly, the benzoin condensation can be performed in a mixture of two different aldehydes, like what I have in the first case. I have aldehyde, let's call it A, and I have an aldehyde B over here, and those are two different species. However, they do react with each other without any problems doing the benzoin condensation. The more reactive aldehyde, in this case it's going to be the aldehyde B, so more reactive. So normally the more reactive aldehyde is going to act as the nucleophile in this reaction. Likewise, if you have a mixture of an aldehyde and a ketone, like what I have in my reaction number 2, so reaction 2 over here, I have an aldehyde and I have a ketone groups reacting with each other. So in this case, the aldehyde is going to be eventually your nucleophile. And on top of that, we can also use the benzoin condensation as a cyclization method, like in the reaction number 3. So reaction number 3 over here, I'm using that as the cyclization, and in this case I'm making a new 6-membered ring by performing the intramolecular benzoin condensation. And as I mentioned before, that using the chiral catalysts can make certain stereoisomers, in this case very stereoselective, because if we look at all of our products, we have a chiral carbon over here. We've got a chiral carbon here, and we have a chiral carbon over here. So using the chiral catalyst instead of just a regular cyanide can potentially give us one stereoisomer versus just a 50-50 mixture of both possible ones, which can be vitally important for medicinal chemistry and synthesis of biologically active molecules as well. And this reaction generally is an equilibrium, so that's another thing that I want to point out here. So if you somehow manage to make an alpha hydroxycarbonyl, and alpha hydroxycarbonyl is going to be any molecule where you have a carbonyl and you have the OH in the alpha position over here. So if you make an alpha hydroxycarbonyl somehow through some sort of chemical magic, then you can potentially open up this molecule and break this bond via the retrobenzoin condensation. However, making such an alpha hydroxycarbonyl is actually not a simple task. So I haven't personally seen anyone doing the retrobenzoin condensation except for the purposes of, scientific curiosity. Anyways, hope you guys enjoyed learning about this little neat reaction, and Let me know if you've ever heard about it before or if you've covered it in your course, and I would like to hear about that. If you like this video and want more content like this, please make sure you subscribe, like, and share this video with your friends and classmates, and I'll see you in the next video, and until then, remember to stay awesome!